Hi class, I thought since it's been a little while that we could review a couple of key terms and concepts from this past unit. So the first one I'm going to be reviewing is normal distribution. Normal distribution is that bell curve. It is an important assumption for our hypothesis testing. With the normal distribution, you see the majority of scores are in that middle range. It's reflecting the mean and the median and the mode, which we're going to talk about in just a minute. So normal distribution, again, bell curve, something that's needed for us for one of the assumptions for the test that we're learning about this semester. When we talk about finding an average or using descriptive statistics, we're referring to central tendency. So central tendency, our three options are mean, median, and mode. Mean is the fulcrum, averaging out all the scores and dividing by n. This is our most commonly used average or measure of central tendency. It takes all scores into account. The median, like the median in the road, is the middle point. The middle point does not take the most extreme scores, is not impacted by extreme scores, and it is the middle value. The mode is your most frequent score, and again in the normal distribution all of those would be approximately similar. Along with descriptive statistics, besides the average, we want to know what spread, how much variance is going on with my data set, or the dispersion. For these, it's the range, the variance, and the standard deviation. Range is the crudest measure, highest minus lowest. We don't really use that one very often. Variance is useful, but variance is S squared for sample or sigma squared for population. It's a little bit harder to interpret. So my favorite is standard deviation. Standard deviation is S for sample or sigma for population. It refers to the average deviation score, and so it is taking into account what's going on in your spread. A large standard deviation means that you have a lot of variance going on. A small standard deviation means that you don't have very much variance going on. And a standard deviation of 0 indicates that all your scores are the same. There's not any differences between those scores. When we're looking for and identifying outliers or extreme scores, we could use Z. So Z is a way to standardize our scores. You can have a raw score and then you can go through and standardize it. Why would we want to do that? Well, it allows us to compare apples and oranges. It also allows us to have a better idea where that score is in the distribution. So a Z-score takes into account where that score is in relation to the mean, as well as taking into account the spread or the variance that's going on. So it's something where in the formula, if you remember, it's x minus mean over the standard deviation. A z-score of 0 means that the score that has a z-score of 0 is the mean. If I have a z-score of -1, it means that my score is 1 standard deviation below the mean. If I have a z-score of 2, it means that my score is 2 standard deviations above the mean. So a z-score standardizes those scores, and when you go to interpret a z-score, you can interpret it as units from the mean. When we're going through and defining outliers or extreme scores, we've defined them as scores outside that -3 to 3 within our z-score ranges. The next thing that we're going to talk about is hypothesis testing. Hypothesis testing is looking at what steps that we take. So the first thing that we're doing is identifying our population. When we run inferential statistics, you take data from a sample and draw inferences or generalizations to that population. After we do that, we're going to come up with 2 hypotheses. The first one is the null hypothesis, the nada, null, nada, never, nothing changing, nothing's going on. boring hypothesis and your research hypothesis. Your research hypothesis is one where you're predicting change, you're predicting possible improvements or a decrease or some sort of differences between your groups or relationships. For some statistics, when we go through and set up our hypotheses, we'd be basing it off of a directional or a non-directional research hypothesis. So I'm going to go into that more in just a minute when as it connects to one-tail and two-tail tests. For your null hypothesis, again, that's the one where we're expecting nothing's happening, nothing's going on, there's no relationship, there's no change. So oftentimes you can take your research hypothesis and put a no in that wording to fit the null. Once you have your two hypotheses, you're going to be finding your critical values or critical regions. Your critical regions are telling you this is where I'm seeing impact, this is where I'm seeing change, this is where I'm seeing differences, this is where I'm finding statistical significance. To find that critical value and identify that critical region, again, that's going to be that outer areas of your distribution, because that's something something unique is going on. It is based on the alpha level you set. So you set your alpha 0.01 or 0.05. It also may be dependent on if you have a one-tail or two-tail test. Again, that's connecting to having a directional or a non-directional research hypothesis, and we're going to go over that in the next slide. Then you're going to calculate your test statistic, whether it be the z-test, the t-test, or perhaps F for ANOVA. Once you've calculated that, you're going to compare where does that fall in my distribution. Is it in the finding significance, critical value, critical region, or is it not? And once I've made that decision, if it's not in the critical region, I make a decision that I have failed to reject the null. Failed to reject the null is a double negative, and it basically means you did not have significant findings. You see no differences. There is no relationship. If you have your finding in the critical region, past that critical value, you've made the decision reject the null. This is the exciting one. This shows you have support for your research hypothesis. Once you've made that decision, again, you're either going to say fail to reject the null or reject the null. Then you're going to draw a conclusion back to the context of your study. So giving us some more explaining what does this mean, reject the null, in terms of the experiment that was run or the study scenario you were going through. After you've done that, regardless of which decision you made, you would do effect size testing. So that could be Cohen's d. Remember, effect size relates to how strong are your findings, and again, it's calculated regardless of the decision you made. So let's go back to this idea of directional and non-directional research hypotheses. So again, some statistical tests that we're going to run are going to have an option to do a one-tail test or a two-tail test, because we're going back to that normal distribution of that data. When I am running a one-tail test, I am running a directional test. What that means is I've chosen to make a prediction for a specific direction. I predict increase in happiness scores. I predict a decrease in pain. So I'm putting, if my alpha was 0.05, I'm putting all of that critical region, all of that 5% area on one side. If I have a non-directional test, now I could be predicting an increase in happiness, but I'm not going to put all my eggs in my basket. I'm going to take a more conservative approach. So what's commonly done is a non-directional test. A non-directional test is I'm predicting change, I'm predicting differences, I'm predicting that something is going on, but I'm not going to say which way it's going to go. And so I'm going to take that 5% and I'm going to divide it between two tails. And so you have a two-tail test, which means you're going to have two critical values. Directional, one critical value, non-directional, two critical values. So then we are going to go through and talk about connecting to effect size. So effect size is looking at how big is your effect. Effect size relates to power. Power is your ability to detect significance. If I have, you want more power. So things that will give me more power. If I have a larger sample size, that is going to give me more power. If I have a large effect size, that's giving me more power. If I have a p-value of 0.01, that will give me more power than a p-value of 0.001. 0.01. If I have a p-value of 0.05, that will give me more power than a p-value of 0.01. The graph or the figure on the right hand of the slide shows you some of the things that get into and connect with power. So if a two-tailed test is not going to have as much power as a one-tailed test, though it is a more conservative, more common approach. We already talked about significance levels, and we already talked about increasing sample size gives you more power. The more people you're collecting, the more likely you're representing your population. And it's also giving you more power. The stronger your effect size is also giving you more power. Some things that connect with effect size, which we're going to get into more as we talk about different designs. If I have a between group design, which means I'm comparing one group that got headache medication, one group that did not get headache medication. If I have a large effect, I typically have larger group differences. When I'm comparing those two groups, headache and no headache, again, different people in each group, I would see that greater difference between group differences is going to give me a larger effect size, which also is going to give me more power. Within treatment variances, looking within those who took the headache medication, looking within the group of those who did not take the headache medication, I do not want a lot of variance going on between those groups. Everybody who took the headache medication, I hope, responds similarly. Everyone who didn't take the headache medication, I hope, responds similarly. So a decrease in within treatment variance is going to give me a larger effect, and we're going to get much more into this when we get into ANOVA, analysis of variance. The other thing that is important to review is that sometimes I can make a decision based on my hypothesis tests, and it's inaccurate, it's wrong. And so again, we talked about type 1 and type 2 error. Type 1 error is this idea that you're saying, I found something, I won. So type 1 is I won. You're saying reject the null. Reject the null means that you found significant differences. You found an effect. And then in a type 1 error, that's wrong. And so sometimes a type 1 error is called a false positive. So in my little figure, this doctor is telling this individual, this male, you're pregnant. So that's an example of a type 1 error. Type 2 error is a case where I didn't find significance. My decision when I ran my study was fail to reject the null. I did not see enough evidence that something was going on. Appears as nothing was going on. So a type 2 error connects with I initially say that I failed to reject the null. I initially say I'm not seeing anything, and in reality I should have. And so in this cartoon you can see the woman is pregnant, but yet the doctor is saying you're not pregnant. All right, so let's connect this back with our hypothesis testing and effect size. So I'm going to go through 3 scenarios and we're going to figure out, do these things match and make sense, or is it a case where we've made an error? So in scenario 1, I've decided I failed to reject the null. I was not in my critical region. I was in that middle area. I failed to reject the null. I had no differences, no effect. However, when I calculated effect size, like Cohen's d, I calculated a large effect. So here I'm saying there's a large effect, but yet my hypothesis testing is telling me I failed to reject the null. So there is a mismatch. I did make an error. What error did I make? We'll discuss that in a minute. Scenario 2, I initially said I reject the null. Hooray! My statistic was in the critical region, so I'm saying I found evidence something is going on there. There is statistical significance. However, when I calculate effect size, my effect size shows I have no effect. So here I have a mismatch. Since I have a mismatch, that does indicate I had an error. What error did I make? We'll get back to that in a minute. Scenario 3, I've decided to reject the null. Hooray! I'm in the critical region. It's showing I have statistical significance. I then go to calculate my effect size, and yay! I have a large effect. Both of these things complement each other. Did I make an error? No, I didn't. Those two things match. It would also be the case if I said fail to reject the null and I have no effect. That also is a match. Those two things complement each other. So let's go back to our two scenarios with the error. Scenario 2, reject the null, but I have no effect. That is a type 1 error. Fail to reject the null, but I said I have a large effect. That is a type 2 error. So I hope these things sum up our big picture ideas for the semester and you're ready to go and carry on. Thank you.